Hello everyone, this is the announcement video for homework 3. Now, in this homework, we have actually plenty of tasks, and if you are going to study for your final exam, this is a good opportunity to do that. Because it is kind of a recap of all remaining topics, you will just solve step by step each task here, and basically you should be good to go. Well, there's nothing much to announce here actually, but I wanted to just make a few points clear so that we are on the same page. Now, first of all, we have question 1. We have a transfer function with delay, and you have to calculate the stability interval for a p-type controller using different methods here. So one of them is the body plot. You have this GS here. Use the body plot to basically calculate the stability interval. Now, when you're designing or when you're answering this question, please use the methods that we use in the laboratory sessions, where I plot the body plot manually, and also annotate the points of interest on the plot itself, and then give also the necessary small steps. For example, we look for, let's say, phase 100 here. So we have the body plot. I annotate programmatically the point where phase is 100. There's a certain frequency, and then there's also the gain there. You might use different colors for different points that you pick. For example, due to the stability interval, you might be interested in multiple points, so give a red color to one of them, the blue color to another of them, so we can distinguish them. Put that plot, don't use directly the body command that generates you the plot. Plot it manually, annotate that point programmatically, and then add just one line or two lines of explanation of mathematical expressions, of course, on how you did acquire that value from the body plot. Why do I tell this to you? Basically because if you follow this rule, you get two things out of it. One of them is a good report that you are going to generate, and the second one would be then to rely on MATLAB as little as possible, because you have to know what you're looking for on the body plot if you're using the body plot. And in the exam, you will be given, for example, a body plot on a logarithmic scale, but then that's going to be it. So I'm sorry. So basically, you won't have the um, power of MATLAB. Therefore, you need to know where to look at and what to gain from that point. So therefore, please, if you're providing a body plot, plot it manually as I do it in the laboratory session, annotate it programmatically, so put in a certain indicator, a marker on that point, using a one line of code, and then also write down what you have used. For example, phase equals 100 for this reason, therefore the frequency is this, and then the gain is that, and I've calculated the interval like this. So give the mathematical steps, don't skip steps. In this case, you don't have to write down 10 pages, 20 pages. It's just 3 or 4 lines of mathematical expressions. That should be good for you. Now, there's the body plot, there's the root locus plot. Again, give the root locus plot, give some explanation. Using the first order Putty approximation is actually, or the second order Putty approximation is about the Putty approximation itself. And once you have done that, you need to use a certain method, an additional method, to conclude the interval here. So be careful about that. But yeah, at that point, you might opt for different options. Choose one of them which you find suitable, and try to find the intervals here. Of course, when you are done with that, it would be a good idea, in my opinion, to give us a small table of the results, like lower bound, upper bound methods, and just plug in the values that will show you something about the stability interval of the system or the tools that you have used. Now, once you've done that, a similar approach is taken for the PI controller. So you will going to be designing a PI controller for 10% overshoot and 10 seconds of settling time. You can use the first order putty approximation, the second order putty approximation. Again, give all the necessary steps. If you're using putty, I would assume that you are going to use the algebraic method here. So use the algebraic method, provide the problem, show the result, repeat it for the second one. Then there's the Smith predictor here, which you should be familiar from your notes with from your notes. That's quite self-explanatory. If you think about the Smith predictor, if you know what it is, it's quite easy. And then there's the body plot. You might need a little bit research for this. Your lecture notes might not be sufficient for this, but there are nice PI controller design methods in the literature. It's a small piece here, so I've added this so you can also experience on this. So yeah. Then, of course, compare the SEP responses on the same plot and the controller coefficients. Comment on the results. This means that you should actually create a nice figure and then assign some colors to these four methods and then use legends for them and show them nicely so we can see if it's similar, if it's not similar, so we can conclude what it is, and then you might give the controllers to see how different they are. I would recommend you to give it in TF and ZBK form so we can see what zero we've chosen or what the coefficients are. So commenting on the results is also important. Most of the time when you do homeworks, I see that the comments are not really helpful because comments on the results are not meant to be just directly telling what's happening here. For example, let's assume that we have a step response. It has settling time of 10 seconds and overshoot of 10 seconds. The following is not a comment. The settling time is observed to be 10 seconds and the overshoot is 10%. Well, that's not a comment that helps us in any way because I can already see that from the plot itself. What I cannot see maybe from the plot is that it is 10 seconds and 10% because the dominance factor is sufficient enough. If I tell the reason, if I comment on the reason of things, that is a contribution, and that contribution is valuable. So any comment is not really a comment. A comment that has a contribution to what's not obvious is the comment itself that I'm looking for. In this case, the comment would be something along the following lines. The party approximations have some pros because this, whereas some pros because we can do this and this. On the contradictory, it's the Smith predictor has this assumption, therefore we cannot do this well, and the body plot is maybe the best one because this and this. So what I mean by that is you should kind of give the essence here so that we can get the idea that is not obvious from the plots. Or if it's obvious, maybe you should explain the reasoning behind that. So, so question one is about delay, time delays, and frequency domain. Now, question two is more about the state space representation, and there's also quite some stuff to do here. So first of all, we have a transfer function. You have to calculate the state space representation ABCD. Now, the calculation of the state space representation is a very specific one. I have talked about this in the laboratory session. If not, I will talk about this in the laboratory session, and you should basically bear with those steps because it is a very specific way of getting the state space representation. I'm not asking for the MATLAB's SS to TF command or any control system toolbox command that does this for us. And I'm also not asking for any canonical form at all. I'm asking for the specific one that I'm showing or going to show you in the laboratory session. Repeat those steps and you're good to go. And after that, we have a state feedback controller design, which should be self-explanatory. I want you to do the steps and show the steps. You have PDA, you have phi C, you will have the whole formula. Just use everything and define everything step by step. Show it in the report. And once you're done with that, For question 2, what you can do is you can just open a Simulink uh, model, create a Simulink model, and use that for simulations. There's a state space uh, block in Simulink available to you. That would be easier for you. The only thing when you're using Simulink that I want to ask from you is to change the backgrounds of your scopes. Make it a white background. Change the line width, please. So pay attention to the styling of your plots because they are most of the time not readable, too much black and stuff. And yeah, please pay attention to that. If you are going to use the comfort of Simulink, please also pay attention to the styling of your scopes and plots. If you don't want to use that, I can understand that. You can also go the coding route, but I would discourage you to do that because at this point, if you're dealing with this homework, you're probably not going to have that much time. So use the easy tools that are available to you. Maybe go ahead and open a Simulink block, just drag and drop, enter the parameters. You can enter matrices into those blocks. You can just have an init.m file in the same folder, call that init.m file, which defines ABCD in this case, and then you can just use those blocks. If you have any trouble, please look for help. You might also ask me in Discord, etc., etc. But when you're providing some plots, please just pay attention to the styling. When I'm providing plots, you see that I increase the line width, I use special colors, my background is white. You should stick with the same in the Simulink model. So here we have an assumption that all the states are measurable, so this doesn't change anything for the state feedback controller, but it means that all that is necessary is available to you. Plot the closed loop step response and states. So since this is a third order system, you should have 3 nice states and 1 output. So maybe having 3 states, 1 output and 1 input as a plot, as a scope, a complex plot would be nice because we will be dealing with that later. So here you're designing a state feedback controller, and as far as I'm concerned, we didn't give you actually anything about the specifications. So what you can do is, if you you can feel free to go ahead and go to Q1 and maybe use 10% overshoot and 10% settling time, or you can just use some arbitrary polls. It's up to you. I'm just interested in the design steps and the results. It's not really about the polls at this point. But if you want to choose something, you can go ahead and use 10% overshoot, 10% settling time, and yeah, design a state feedback controller for that. And the next step is to design a Lundberger observer, which is again one of our topics, which is basically the same as designing a state feedback controller. So for this homework, if you struggle, if you feel like you are doing too much, please keep in mind that some things that are that seem like a lot of work might not be a lot of work at all. So here, the Limburger observer design, the state feedback design, the whole Q2 thing might not take that much long. The only thing that you have to do is study a little bit for state space representation, what it is good for, and how we can use it, what the design steps are. It's just a learning curve, but it's not that difficult. This part, on the contrary, might be the difficult part. It depends upon you, but yeah, just a little comment here. So design a Limburger observer. I again want to see the steps here, but don't overcomplicate stuff here. If you, for example, define PDA in line 1, so if we have PDS, for example, s squared plus 2 zeta omega n s plus omega n squared, you've shown that in one line. The next line can be continued by PDA is equal to a squared plus 2 times zeta times I times a plus omega n squared I, something like that. And then you can give PDA the result. I don't really need all the necessary numerical steps. I just want the steps, not the numerical ones. You can skip numerical stuff. And please use MATLAB to your advantage here, because MATLAB can do all the calculations for you. So the matrix multiplications, the results, everything can be done in MATLAB. So if you run a script and just leave out the semicolons where you're interested in, you can just copy the results into Word and then arrange it to and create a report out of it. So design a Limburger observer. Depending on your state feedback controller, you have to choose specific poles for the Limburger observer. You cannot use the same poles for the state feedback and the Limburger observer. It doesn't make sense. So you have to make a choice here, depending on the poles that you have chosen here. So that's the reminder here. Now, at this point, if you're designing the Limburger observer, the coefficient L is sufficient here. We have coefficient K and the states and set and the output, etc. Here, we will use the estimated states for the state feedback controller, which means that we will combine the state feedback controller and the Limburger observer here. And here Simulink becomes important because what you are going to do is you are going to compare some stuff to each other. But this is a task on its own, and since we are dealing with transfer functions, since we've converted into state space representation, most of the time, or actually we don't have initial conditions, so everything has initial condition 0. But in this case, I want you to change the initial condition of the actual system, of the model itself, of GS, for example. But you are going to use maybe the state space representation ABCD. It should have an initial condition. So you can see compare the results with and or without observer, where the actual system states have, there's a misspell here, initial conditions, and the observer does not. I'm sorry. So there will be a system, the actual system, it should have an initial condition, so it shouldn't start at 0 when the simulation starts. But everything else, the observer itself, should start at 0 so that we can see the effect of the observer if it's estimating the states, if it's not. Because otherwise, if you have 0 initial state for the system, 0 initial state for the observer, they will be on top of each other and we will not be able to see the difference here. So you should apply the initial condition to the system and only to the system. The observer should start from 0. All the states of the observer should start from the 0. So you should basically construct the necessary structures with observer, without observer. You should just compare them and show the results. And that's basically it. Of course, again, how good the report is plays an important role in your grades. So if you are using Simulink, be careful about that. That's basically it, I guess. So, good luck in your homework.